All right, good morning everyone. Thank you for joining the BMS deep dive and specifically the presentation about battery charger design for single cell. Apologize for the delay at the beginning. We had a few technical issues, but hopefully we'll get started now. My name is Miguel Aguirre and I'm the System Engineering Manager for single cell battery chargers out of the BMS group. And what we're going to be talking today is, first of all, single cell charger system. What do we refer to as a single cell charger system? After that, we'll go over input considerations and some of the limitations that we face doing these designs. Some topology options, specifically focusing on power path and non-power path architectures. Some of the thermal issues that you find, then a little bit of some market trends and needs versus the limitations that impose into the design. And then following up with the charge time optimizer feature, which is a new feature we are including on our newer chargers, and we'll show some data about what it does. And then summary and Q&A. So what do we refer to as a single cell charger? Essentially, this is the most common solution out there for smartphone and for the most popular tablets as well. If you look at the top 5 vendors on tablets, about 80% of those by volume is single cell. The single cell, it's essentially a 1S system. In other words, when we refer to a single cell, it's a 1S, 1S2P, 1S 3P, anything single cell, we're talking about series cell. Okay, so some of the benefits of this is allows for a simple low voltage design of your system. Essentially, at a 4.35 volt battery chemistry, you can design everything for that voltage. So your PMIC, your downstream systems doesn't need to support anything higher than that. It's a very simple design to charge from a 5 volt supply, which is pretty common on typically smartphone adapters, USB ports. USB ports today with the USB power delivery, that's going to change in the future. We are always operating in a step-down fashion. And as I mentioned earlier, this is a 1S configuration. You can have a 1S XP configuration. This is all single cell. The same rules applies on the top. The benefit of just doing this is just essentially you're doubling your capacity, right? If you put a 2P, you have double the capacity and so on. So talking on the input side, then the first question that you need to ask yourself is, how many inputs do I really want to support? Do I want to support a single connector that I can use with a USB or wall adapter, or do I want to have multiple connectors where I have an USB connector and perhaps a docking station that connects through a different area? Or do I want to have one input connected to the wall and another input connected to wireless power, for example? Those are the kind of questions that you need to go through. And that's where it goes for the input sources, right? Do you want to support USB Charlie only, which is 500 milliamps for 2.0 or 900 for 3.0? With USB power delivery, these current levels are going higher, but that spec just got released, so there's not a lot of products. There's no products out there today that can provide that power on the USB port. And if you want to support USB Charlie and or adapter into a single port, then some of the limitations that you will have is, for example, the micro USB port. Maximum current that it can support typically is about 1.8 amps. The USB spec actually says about 1.5 is the maximum that they have. Again, this is just USB, not USB power delivery. And with that limit on the input side, then that's going to limit essentially your output current. So here I'm showing a plot of output current, assuming a 3.6 volt battery and 90% efficiency. So if you have a 5 volt adapter limited at 1.5, the maximum current that you're going to get is right about 1.8 amps. As you increase the input voltage, then you can start increasing your output current. This output current right here, I'm talking about system current plus battery current. In other words, that's always going to be split between the two. So looking at adapters then, the most common adapters today for smartphones are typically between 5 watts and 8 watts. Those are the standard kind of micro USB or proprietary connectors. For most popular tablets, it's in the 10 watt to 15 watt range. So what does that mean? So again, if we take a plot of battery voltage, so essentially we're showing a charge cycle or mimicking a charge cycle on the x-axis and assuming a 90% efficiency, and these are different charge currents, then if you have a smartphone adapter, more than 2 amps on a 8-watt adapter, you're going to be able to get it until right about 3.7 volts. After that, that current is going to be lower. If you have a 15-watt adapter, then you can probably get 3 amps all the way through a 4.35 volt battery. Anything other than that, you're going to be essentially limiting the current because of your input side, not because of your charger or your adapter or whatever, or your battery. So essentially, the message I'm trying to show here is, while you're selecting your charger, just make sure that you look at what is it the adapter that you plan to use and how do you optimize this to support the charge current that you want. And that has effects into your physical design or mechanical design of your product as well. So power sources have their limits, right? When we say there is a 5-watt adapter, and let's say that is a 5 volt, 1 amp, those are nominal numbers, right? Potentially it could be a 5 volt, 0.95 amps, it could be a 5 volt, 1.05, or 5.05 volts, 1 amp. There's tolerance on all this, right? So the reality is that all these adapters is going to have their own limits, and this is becoming increasingly important now with standardization of some connectors like the micro USB and stuff like that. So because you never know what the tolerance, or you could know what the tolerance is and you can design your system to pull the lowest of that range, or the other option that you have is using the VNDPM, which is a feature we have in our chargers, to try to solve that problem. So here's an example, right? What is the VNDPM? VNDPM is essentially an analog loop that is continuously monitoring the input voltage, okay? So here I'm showing an example. This is a typical linear charger with power path. You have the input, it's regulated for the system, and then you have a FET that connects between the system and battery to charge the battery. So what VNDPM does is it's looking at this input voltage and it's comparing it to a reference. When this input voltage drops to the program value, we cut back the input current to keep this guy from collapsing, okay? So let's look at an example of a device that doesn't have VNDPM. So what happens here is the input current is being pulled from the system or battery, and it's more than the adapter can support. So what happens is the input voltage starts to drop. When it hits the UVLO of your system, essentially the device will turn off, the adapter will recover, and then it starts all over again. So you enter this hiccup mode where you're hearing brownout and getting out of brownout on and off. So that's what happens if you don't have a VNDPM function. Now, when you have VNDPM function, this is how it looks. So essentially, we have the same thing, a current limited adapter, and in this case, I'm just pulling current from the battery, okay? When I pull that current from the battery, the adapter starts to drop because it doesn't have enough power to support it. You can see here, when it hits the VNDPM threshold that we program, then the charger starts cutting back on the input current, and it regulates that current to whatever that adapter can support at that voltage level, okay? So this is a feature that you will see in a lot of our newer chargers. It's essentially on the ones that are I2C, you can program this level to different voltage values. So power path versus non-power path topologies. So non-power path topology is kind of the traditional design. Essentially, your system and your battery are tied together. So at any given moment, your system voltage is going to be exactly your battery voltage, okay? So what are some of the limitations of this? Well, to start with, if you have a deeply discharged battery, it doesn't matter how much power you have on the adapter, you're not going to be able to boot up your system until that battery gets to the minimum system voltage that you need to operate. The second drawback of this is your charge current is always going to be split between sys and battery, right? So what's so bad about that? Well, the reality is if you cannot predict this system current and adjust it dynamically, or adjust the iCharge dynamically, what you're going to have to do is program a charge current that is defined by your battery manufacturer. Say you have a 1 amp battery manufacturer and they're telling you cannot charge more than 1 amp of charge current. So that means this iCharge needs to be programmed back to 1 amp. If the system needs 200, you're going to be putting only 800 milliamps into your battery. So that extends your charge time. And not only extends your charge time, but if you want to terminate, say, at 100 milliamps, but during quiescent current, your system is taking 200, you will never terminate because your charge current is always going to be above your termination current. And the fact that that slows down the charging, again, if you cannot dynamically adjust this based on your load requirements, then your safety timers could potentially expire as well, depending on how much current your system is pulling from the battery. When you go to power path, then now we have split the two. We have, in this case, a converter, and this doesn't necessarily need to be an SMPS. It could also be just a linear LDO kind of thing. And then you have a charger. Okay, so here we know exactly how much current is going into the battery, and we provide the system current, whatever that current may be, as long as your adapter can support it. So the benefit here is you can set this converter current to whatever value you want that guarantees that you're going to get the charge current that you need, assuming your adapter can support it, and provide your system load. So because we know exactly how much current is going into the battery, it doesn't matter what you program this to, okay? So let's say you program this to 1 amp, your adapter can give you 2 amps. You can just program this converter current to be 2 amps. We will make sure that only 1 amp goes into the battery, and we will provide whatever the system needs, okay? The reality is you program this current on the input side. So anything that the adapter can provide will go to the system. The other thing is now you don't need to worry about necessarily adjusting this current with dynamic loads because, again, the charger is taking care of limiting that current into the battery. And you can always have an accurate termination at that point as well because, again, you always know how much is going here. The other benefit of this architecture is, let's say you have a current limited adapter, you have a 5 watt and your system sometimes needs 7 watt when you're charging and running your system. Well, this automatically will cut back this current and give priority to your system. If we know we are operating in that and we will know that we're operating in that mode, we can extend our safety timers to account for that time that you're not putting all the current that you want on the battery. So essentially the charger is making the decision or could make the decision of just extending that charge time and making sure that you don't prematurely expire the safety timers. So just kind of going a graphical representation of what we were just talking about. In this case, I'm showing an example of a 1 amp adapter. 500 milliamps are going to the system, 500 milliamps are going to the battery. Now your system needs more current, okay? It needs 800 milliamps. So what happens is we still have only 1 amp available. So the charger would automatically set this to 200 milliamps, okay? When that system requirement goes away, then essentially we go back to the program charge current and your system current, okay? So let's put these two together. In this plot, we're actually showing VNDPM and DPPM, both of them working together at the same time. So we have a 750 milliamp adapter. We're charging the battery at 750 milliamps as well. And we have 0 load on the system. Now all of a sudden, you need 1.2 amp on your system. So the first thing that happens is that input current increases and you see the input voltage starts to drop, okay? When that starts to drop, this, at the same time, this is also falling. Why is it falling? Because you only have 750 milliamps. So your system starts to drop, we cut back on the charge current to give priority to your system. Now the adapter fell to V in DPM. So we scale back the input current, we continue to take current from the battery, and we enter what we call supplement mode, which essentially means we are discharging the battery to provide that system current that you need. So you can see the current going to the system stays relatively flat. That means we're always giving that priority to the system, and the system voltage, this dip right here, is typically limited by the battery voltage, or battery voltage minus the RDS on of the battery FET. Once that low requirement goes away, your system recovers, the charge current starts to recover, your input current recovers, and your input voltage recovers again. So we go back to charging the battery at 750 milliamp, which was the original target, and essentially everything continues to operate normally. So the nice thing about this whole thing is the software doesn't need to do anything. This is all handled by the charger analog loops. So once you program the V in DPM limit, the charge current that you want, the input current that you want, everything else will be handled by the analog loops on the charger. So a question that I get a lot is VNDPM then the same as DPPM? And the reality is no, they're two completely different things. VNDPM is focusing on the input voltage and making sure that your adapter doesn't crash. Then DPPM is looking at the output. In other words, your system, your battery, and then managing the power between the two outputs. DPPM, allows you to know exactly how much current is going to the battery, so that's where it allows you to have accurate termination, prevents safety timer expirations, and so on. And another question that I get a lot is, so which one is better? And the reality is it really doesn't matter. It depends on what you want to do on your system. Do you really need power path? If you need power path, then you may not. If you don't need power path, then you don't need DPPM. VNDPM, if you know that you have some adapters out there that maybe third parties are doing adapters that are not as good as what you provide with your product, then VNDPM may be a good feature to have. And if you want to be able to extend your safety timers or have accurate termination, then DPPM may be a feature that you want to, or if you want to just power it up when a battery is completely dead. Oh, there we go. All right, so thermal regulation and protection loops. On all the TI chargers, you're gonna see that we have two features. One is thermal regulation, one is thermal shutdown. So what is thermal regulation? Essentially, thermal regulation, you can think about it as a power dissipation regulation as well. So what it's doing is looking at the temperature of the IC. And if the temperature of the IC gets to that thermal regulation point, then we're gonna cut back on the input current to maintain a kind of a level set power dissipation on the IC, okay? So here's an example. Essentially, we're just increasing the voltage on the device, and we're trying to see what happens with the temperature. So as we increase the voltage, the temperature is increasing, then we stop increasing the voltage because we got to that point, and what's gonna happen is the charge current starts to go down, and it falls to whatever the temperature, whatever the current needs to be to maintain that temperature. Now, as the battery voltage increases and you have less power dissipation on the IC, then this current starts to go back up because we maintain that temperature. Or if your system, say the reason it got hot is because the backlight was running at 100% brightness, and now you turn off the backlight, the ambient will start to drop, therefore the IC will start to drop as well, and you start increasing the charge current again. The other feature that we have then is thermal shutdown, and that's more of a fail-safe. In other words, if the thermal regulation kicks in and is pulling all the current down to zero, and the temperature continues to increase because of ambient or something else, then we'll go ahead and completely turn off the charger. And that's more of a protection to ensure that no damage has happened to the charger itself. So one parameter that is you see on a lot of datasheets and a lot of competitors also use this number is the theta JA, right? And as defined by this JDEC spec, this is the factors that affect theta JA of your system. And PCB design, of course, it has the highest correlation, right? This is nothing new. Chip or pad size has a big correlation as well. The smaller your IC, then the less area you have to dissipate heat. And then there's some other factors that playing into it as well. Altitude, external ambient temperature, power dissipation, all that. A lot of people use this number to approximate what the IC temperature is gonna be. And that, it's kind of a good rule of thumb, but it's really not the intention of this. And it doesn't necessarily gonna give you accurate numbers. But it can be used for comparison purposes. In other words, you can see a device that has a theta JA of 45 and a theta JA of 40. In theory, then that device that has 40 is going to typically run a little bit cooler than the one that has 45. So this is a case study we did with one of our charger ICs, okay? And the idea was to see what the thermal effect is on a PCB design based on theta JA. So the device is a 2 millimeter by 2.1 millimeter WCSP. And we took a high K board with no thermal bias as defined by this standard, and the results we got was 69 degrees C per watt. Now we took the same ICs and we used 2x2 thermal bias, again as defined by this standard, and the results were 45.4 watts, or degrees C per watt. So you see there's a big difference between the two, and what I'm trying to show here is when you see these numbers, you need to make sure what are the assumptions that are being made, because this can be very misleading, right? This is the same device, and if you see these two numbers and I don't tell you anything, you want to say, well, I want this one. It is the same device. It doesn't really matter. All right, so now let's talk a little bit about market trends and needs and limitations. So we went back and we looked at a year and a half or so worth of data for smartphones. And what we're looking at is a couple of factors: product thickness and battery size, right? So if you look at new phone by introduction date on phone thickness, I mean, nothing surprising here. You're seeing all these smartphones are getting thinner and thinner and thinner as time goes on. Now, if you look at battery capacity, the trend is different, right? And again, no surprising, there's more features, there's more different screen, high resolution camera, so a lot of different things happening that requires more power, okay? The interesting point is this. If I take the same phones and I look at it, right, for example, HTC One X, the thickness of the phone itself is 8.9 millimeters. If you look on the web, that's what you're gonna find. The battery is 4.4 millimeters. That's almost 50% of the thickness is coming from the battery, okay? If you look at the Galaxy S3, 8.6 millimeter, 5 millimeter thick battery. Again, that's more than 50%. And if you look at the Galaxy Note, 10 millimeters, 6 millimeters is the battery. So 60% of it is coming again from the battery. So what does this tell you is, you want to make your phone designs thin, you have 60% of it going to the battery. Now you have 40% left for LCD, components, inductors, connectors, antennas, everything else. So that's not a lot of space available. So when we saw that, what we said is, okay, we need to figure out how we can help then. And what we decided is, let's see how we can work around trade-offs. So increasing battery size means larger charge current, right? You want to maintain or improve your charge time. Decreasing product thickness means thinner inductors, which means lower charge currents. So you have two features or 2 points that are pointing in different directions, right? One tells you more current, the other one tells you lower current. So based on this, then what we have seen is, in the case of smartphones, then a 2 to 3 amp charge current provides a sweet spot or for a good balance between the two. And the reason for that is, if you look at the inductor sizes, a 2 amp inductor you can find today for about a 1 millimeter height. This is a 1 microhenry inductor. 3 amp inductor, you can find it for about 1.2 millimeter height. If you start going above that, you go to 2 millimeter or above, depending on the currents that you need. So we said, okay, so what we need to do is then look at how do we make our converters stable for 1.5 microhenry or 1 microhenry. And in some cases, we're actually looking already at 0.47 microhenry. It's a trade-off that you need to make between ripple current and your efficiency that you want. And the other area that we focus on is then how do we improve the charge time, and that's where the charge time optimizer comes into play, and we'll talk about that in the next couple of slides. So what is charge time optimizer? Well, charge time optimizer is essentially a modified topology of the switch mode charger. And its main role is to extend the CC period and minimize the overlap between CC and CV, okay? This is constant current and constant voltage. So previous chargers without charge time optimizer will start reducing charge current way before it gets to that CV value that you programmed, okay? So let's look at a high level block diagram. So this is a kind of a very simplified version of what a switch mode charger looks like, in this case with power path. So you have a bunch of loops controlling the PWM at any given time, or let me rephrase that. There's a lot of loops, only one of them will be controlling, but potentially any of this could start controlling the PWM. So you have the power fetch logic, you have the PWM comparator with the ramp, error amplifier, and then the analog loop selector. So this is an area that takes all this device and fits it into the error amplifier. So when you're looking at the transition of CC and CV, these two are the loops. that are handing off. Essentially, you're controlling here and you're handing off to this guy. Okay. What charge time optimizer does is we redesign or remodify how this handoff happens here and these two loops to try to extend that CC time, and we will show it on the next slides. So this is available on our newest chargers, the 25X and 26X, which are going to production in December, January timeframe. So here's a charge cycle with no charge time optimizer. Okay. So we have the blue line, which is the battery voltage, and the light blue line, which is the charge current. So right here, you see that the battery voltage is not at the CV value yet, but your charge current is already starting to decrease. The charge you're putting on the battery is essentially the area under this curve, right? It's the area of the charge current, under the charge current plot. So if you could extend this, then you're increasing the area, therefore you're putting more charge into the battery for the same amount of time. So in this particular case, we're seeing about an 83 millivolt overlap, which means you're reducing charge current about 83 millivolts before you wanted to, or the ideal case. Now here is charge time optimizer. This is data that we took on the 2426X. So here's the charge current. The yellow line is the charge voltage, and the orange line is the system voltage. This is a charger with power path. So here you can see we maintain a flat charge current all the way to the point where we enter CV mode. The reality, if you look at this data, the overlap between CC and CV is about 6 millivolts, whereas before we were seeing 83 millivolts. So we have essentially extended this by about 76 millivolts actually. And essentially, as you can see, then this area is maximized, therefore you're putting more charge current for the same amount of time into the battery. So if I just take a few snapshots, this is almost a 7,000 milliamp hour battery with a 2.5 amp charge setting. For 50 milliamp termination, you're charging the battery in about 4.5 hours. If you take 500 milliamps as your termination, and a lot of people use 10% of your C value as a termination point, here I'm talking 500 milliamps, which is less than 0.1 C, and we're charging just about 3 hours and 10 minutes. So this is reducing that charge time by just having that handoff. And on this next slide, then I'm showing two side-by-side comparisons. So the red line and this line right here, it's charge time optimizer, and this green line and blue line, it's the traditional approach. So you can see for the same battery, same charge current, and assuming a 300 milliamp termination with charge time optimizer, you get about 2 hours and 25 minutes. With no charge time optimizer, you get about 2 hours and 52 minutes. So that's about a 15% shorter charge time just by using the feature. And the nice thing about it is you maintain the charge current, so you don't need to change your adapter. You can keep your same adapter, same design, just use this feature and have faster charge time. This was an example of one battery that we have. We plan to continue to doing a lot more batteries to see how this results looks like. But we expect, just because the inherent topology that we're using now, that this time will be about that or a little bit better. The other area that we looked at is how can we help, now that we optimize the charge time, then we want to try to expand or extend that runtime when you have no adapter connected. And on a power path charger, right, you have a FET that goes between sys and bat. We already looked at this before. So when there's no input, the current is being supplied to your system through that battery FET. So one way to extending the runtime is reducing this resistance of this FET. I mean, if your system has high transient events, say a 5 amps, and you have a 40 milliamps, 40 milliohm resistor, that means you're going to be dropping about 200 millivolts. So if your battery is sitting at 3.6 or 3.5 volts and your minimum system voltage is 3.4 or 3.3, you are dangerously close to that level and your system may turn off. So in order for us to extend that, what we did is we designed this battery FET now to be only 11 milliohms. So even if you have a 5 amp spike, you have 55 millivolts of drop only. Now, in the case that this 11 milliamps is not enough, you need a lower resistance on this 26X family, then we also provide a driver for an external PMOS. So that FET will connect between your system and your battery, and it's going to be in parallel with the internal FET. So essentially you have two FETs in parallel. You can decide if you need to use that and lower that resistance. So summary, we believe that charger solutions or using charge currents greater than 3 amps on smartphones, it's going to be definitely increasing the thickness of the design. We've been working with a lot of cold manufacturers to see what could we do. I mean, one idea is you can maybe grow the X and Y of the inductor. The problem with that is if you look at a smartphone board, there's really not a lot of real estate left. It's pretty well packed already. The other aspect is thermal management can become a problem because of heat being generated, right? If you have, say, even 3 amps today, 3 amp, 4 volts, that's 12 watt of output power that the charger is spitting, and that is still not counting for your backlight, your chipset, your PMIC. So there's a lot of heat being generated with very little real estate to extract that heat. And focus on reducing charge time, we believe is the best benefit we can provide you guys to maintain, shorter charge time with your current adapter and your system design. And that you're going to be seeing that on these 2 new products as they roll out later this year. And the other aspect that we want you to take away is, we're increasing this runtime by just reducing that discharge path, providing 11 milliamps integrated, and if that's not enough, then we provide the external battery driver, FET driver. That's all I had. Is there any questions? Yes?
So the way you accomplish that is just by pumping in a higher voltage for longer time. You go beyond the 4.2 or 4.35 volts or whatever it is to maintain that current longer, and then you just drop it.
No. So the question is the way we are achieving that is by increasing the battery voltage, the charge voltage, sorry, to get more current. The answer is no. Let me go back to the plot. So this yellow line is the battery voltage, the actual battery voltage.
But the charger voltage is higher.
No.
So how are you going to create the potential difference to pumping this current?
So the difference is we're not increasing the charge voltage, we're changing the topology. So the problem is, in the past, let me go to the previous one, it's easier to see it. Right here, because of this analog loop selector, in order to maintain this stable, because you have a lot of loops going in, you have different gains, okay? And it gets to a point where these 2 guys are trying to control the PWM. And who's gonna win is the one that gives you the lower duty cycle, okay? So because of that overlap that is happening on the analog loop selector, then you are essentially starting to reduce when you don't want to reduce yet. In the new topology, then we redesign how this analog loop selector looks like. So we maintain the same charge voltage. You program, the charge voltage. If you program 4.2 volts, we're not going to go above 4.2 volts.
Right, and I'm not saying that you should go above 4.2 volts on the battery, but you know, especially when you're charging at high current, you're going to have a voltage drop on the wire and whatever. So the charger might think that it's putting out 4.2 volts. The battery is only seeing 4.15.
That is correct.
Whatever. So what I'm saying is, in order to maintain, and this is something I thought about years ago, but in order to maintain the current and minimize, basically charge time optimization, the easiest thing to do is just, monitor the battery voltage, with a smart battery you can do that.
Right.
Because you're getting that data directly from the chip, from the gas gauge. But, have the charger provide a higher voltage so it compensates.
Gotcha.
loss,
Yeah.
right?
You're right. So
Circuitry in the board, at the fence, whatever.
that is correct.
Kind
Yeah.
of Kelvin sensing.
That is correct. So it's essentially, so we're solving two different problems. The one that you're talking about is compensating for the losses on your system and design. So the one that we approach with charge time optimizer is the internal problems. In other words, the handoffs between the loops. Now what you're talking about, there's two ways that we do that. We have a feature that we have on some of our chargers called the IR compensation that essentially achieves that. It programs a slightly higher voltage. The other one that we have is a lot of these chargers have I2C communication. So because you have the smarts,
And you need the smarts.
that is correct. That is correct. That is so there are two different problems that are being addressed, right? Even on that one, you can do that, but you still have the early handoff happening because you don't have the charge time optimizer. So
Once you get to 4.2, you.
exactly. So and the nice thing about it is because you have I2C here, you can get the benefit of both. If you still have the smarts, you can implement that method, plus you get the sharp handoff, and your charge time gets even shorter at that point. So that's a very good point. Yes?
So within the analog loop, is there like a comparator that handles more of the switchovers? Because basically you're talking about the accuracy between the switchover from constant current and constant voltage, right?
Mm-hmm.
So instead of doing an analog loop where you're looking at gains, or you're having more of a threshold, then where it's a constant current, constant voltage level, and it's okay, I'm at that level, switch over now.
Right. So we have actually tried. So the question is, do we have on the analog loop selector a comparator that is essentially trying to decide when to hand off between one or the other? We have tried that already on our previous chargers where we have this one, essentially some of the ones that look like this, because you can still do that, but even that comparator will have its own accuracy. So what happens is, as soon as you cross it, then the comparator says, okay, now I can enable, let's say, my CV loop. But what happens is then you have a drop on the charge current because you still have that overlap between the two. So you are essentially trying to move that problem a little bit away, and the tolerances of that comparator auto reference are going to have the same effect. So what we decided is do it completely different. We don't even use that comparator to try to reduce between one or the other. We just completely redesigned the analog loop selection.
Just curious, so you showed some data on the HTC phones and the battery
Yeah.
thickness was like 40%,
Yeah.
right? So if you take the iPhone, for example, right, they have cut out, and the phone is actually, the battery is actually as thick as the phone because the PCB is going around the battery. Have you done studies on the heat, on the charger and stuff, when the system is designed like a cutout PCB versus like the Droid where the PCB is parallel with the battery? Have you done any?
No, we don't have that data, mainly because it is a little bit difficult for us to collect that thermal data because we will need to open, for example, the phone, and the moment you open it, you're changing the environment. You can try to close it again, but thermal pictures are not going to be very accurate because the reflectivity of the phone material will show different results. We even took some chargers, just the charger itself, where we took the backside coating, and the same charger I see on the same board, we took thermal pictures, we got completely different results because the reflectivity is different. Now, you can try to put a thermocouple, but then you need to find a way to completely close it and make sure that there's no air intake into it, because the moment you have some air going into, you change your environment, essentially. So we don't have necessarily that data.
Yeah, I'm just trying to understand which would be a better, obviously doing a cutout would be better for the battery, but
Right.
for the system design, PCB design, and heat in a charger,
Right.
it's less real estate, so is that
Essentially, yes. And I will expect the cutout will probably have a little bit worse thermal because you have less area to dissipate your heat. You're right.
So do you have a charger that provides you other type of smarter charge time optimization that we were discussing earlier?
The charge time optimizer is included on the 25X and 26X families.
But the one that I mentioned about
Yeah. So these two, you can do it through I2C.
Okay.
The one that has the automatic adjustment doesn't have the charge time optimizer because it was done earlier than this. And what we're looking at, does it make sense for us to combine the two, or does it make more sense to just use the smarts already on the battery? Because nothing, the charger is never going to have as good accurate as the battery, as the gauge, right? So we can try to adjust for it. We may be getting close results, but the reality is we can never predict how that impedance looks like. The other area that we're looking at for the future is then, as he pointed out, providing a Kelvin connection to the battery.
Well,
That's pretty much.
Yeah, that could be another way to do it, but I mean, you can indirectly do that for the smarts, the I2C.
You can do it too, correct, yeah. And that I2C is available today on both families that have the charge time optimizer integrated. Any other questions?